Hello, everyone. Let me first offer a very warm welcome to all participants and speakers to this first lockdown webinar event of the Natural Capital Seminar Series. My name is Deanna Donovan. I'm the economist here at JNCC and the host of the series. Today's seminar is entitled Hidden Sinks, Understanding Blue Carbon. More than 4/5 of global carbon circulates through our marine ecosystems. Ocean and coastal habitats sequester carbon from the atmosphere via seagrass, salt marshes, mangroves, and kelp forests, among other things. These systems lock away carbon at a much faster rate than the world's terrestrial forests. Their protection, therefore, is vital in the battle to mitigate climate change. Today's presentations will explore this one aspect of marine natural capital, namely its carbon value, which is becoming increasingly important in valuation and natural capital accounting related to these assets. A better understanding of this subject will assist us in the realization of multiple objectives related to marine resources management, including the goal of biodiversity conservation. Our speakers today on the topic of blue carbon are, in order of appearance, Dr. Dan Bailey, a marine ecologist and former JNCC staffer, also UCL researcher, who is now working on a project with the South Atlantic Environmental Research Institute, or SARI, in the Falkland Islands. Second is Dr. Tiziana Lucetti, an environmental and ecological economist specializing in coastal and marine ecosystem services valuation and management. She is principal economist at CFAS, a recent collaborator with JNCC on a project on marine and coastal natural capital accounting, and also an honorary lecturer at the University of East Anglia. Finally, we have Professor Nicola Beaumont, also an economist, also working at the interface between natural sciences and socioeconomics. She heads the Sea and Society program at Plymouth Marine Lab and is on numerous national and international committees addressing marine issues. As usual, our three speakers will each present their case for 10 to 15 minutes. After all presentations are completed, there will be an opportunity for questions and discussion. Participants online may submit questions at any time via the chat function in the webinar system. Joe Hawker will be assisting me with technology today. If participants online run into any problems, they may contact Joe through the chat line for assistance. And now I hand control back to Joe, who will invite our speakers to begin. Thank you.
Great. Thanks for joining the webinar, everyone. Today I'm going to be talking about giant kelp, blue carbon storage, and the sequestration value in the Falkland Islands. And so this is a bit of work that I was doing a couple of years ago. Oh, there we go. And it's part of a larger project where SARI, which is the South Atlantic Environment Research Institute, we're trying to look at the overseas territories that are found across the South Atlantic. And so the UK has a number of overseas territories which are have a high resource of biodiversity and ecosystem services that are valuable to society. And so we were looking at these 5 that are in the South Atlantic. So that's up in the top, you've got Ascension, St. Helena, Tristan da Cunha, South Georgia, and then Falklands right at the bottom next to Chile and Argentina. And so we want to look at what kind of natural capital resources they have and some of the ecosystem services that they're providing that aren't currently fully accounted for society. And so I'm a marine biologist, and the work I was doing was looking at the marine systems surrounding the Falkland Islands. And these are quite unusual in that they're fairly unimpacted in a sort of global setting. They're really rich in marine life. And dominant architectural or keystone species structuring the habitat around these rocky areas is the giant kelp forests. And if you're in the UK, you might know kelp. So we have large amounts of kelp surrounding our rocky coasts. But these ones in the Falkland Islands are considerably bigger. So while we have kelp park surrounding the UK, that may be about 1 meter tall, these ones go up to around 10, 20, even 30 meters tall, and go down quite deep, up to about 50 meters depth. And these are home to many marine species, such as fish and invertebrates, large charismatic marine mammals, such as that cute seal that you're seeing in the corner. And these systems, not only are they home to a lot of biodiversity, they're also very valuable in terms of the services that they provide to us. And so there's a lot of direct ecosystem services. So in terms of fishing, so it might be commercial or recreational, subsistence fisheries, because you get these kind of habitats in temperate areas across the globe. So both in the southern and northern hemisphere, around California, they're very famous for it, South Africa, Australia, and then over in the South Atlantic around Chile and the Falklands. And so often in areas like California, it's also valuable for ecotourism, so people diving in these amazing systems. But there are also indirect ecosystem services, which typically aren't fully accounted for the services that they provide. So this might be in terms of attenuating storms and wave damage around coastal areas, or it might be buffering climate change through fixation or a sink for carbon, taking excess nutrients from the water, at home to biodiversity, and this resource for science, research, education, and recreation. So I'm just going to talk about one of these indirect ecosystem services, so the carbon fixation. And when we're talking about marine carbon sinks, we term it blue carbon. So this is kind of it's essentially a bit of a buzzword, I guess, in recent times, where it's the name for any vegetation that effectively takes carbon dioxide out of the atmosphere and stores it either in its vegetation or in the surrounding sediment. So the soil or the sand surrounding those areas. And typically when we're talking about them, I'm sure the other presenters will go into this in more detail, we're talking about things like mangroves, salt marshes, and seagrasses. And these are really significant systems. They cover a large area of the globe and take out significant amounts of carbon from the atmosphere and store it away for a long time. And so, typically we're talking about these kind of ecosystems, but often we forget about a large contributor, which is also macroalgae. So down in the South Atlantic, we don't get these, mangroves or seagrass, these tropical forest ecosystems. But we do get a lot of macroalgae, this kelp system. And so previously, this was kind of a missed area because they typically grow on the rocky substrates, and so they don't have surrounding sediment which can trap these kind of trap and store or sequester carbon away. But more recent research has found that there's quite a significant amount that's taken away into the surrounding areas around the kelp ecosystem and drawn down into the deep sea and buried in the sediments there. And so there's a few mechanisms in which they can do that. So you've got your main kelp system up in the top left. And so as this grows and gets damaged in storm and senesces, so each year it loses its fronds and they get lost into the water, these are either eaten or broken down into dissolved organic carbon or particulate organic carbon. And these are eventually taken down into the surrounding deep sea burial. So it's not all of it, it's only a small portion of it, but when you attribute that to the overall amount of kelp that is in that system, it's a significant amount of carbon that's actually taken down into that deep sea. And the global estimate a couple of years ago was around 173 teragrams of carbon annually, or something like 635 million tons of carbon dioxide equivalent per year. So it's quite a sizable amount when you apply it to all the macroalgae that exists around the coast of the world. And it's been underappreciated until fairly recently. And so we wanted to look at this sequestration and storage within the Falkland Islands. And so the tricky part of this is actually trying to figure out how much is there. Normally when you're looking at a kelp forest, you just see this kind of layering or rafting of kelp on the sea surface. And so it's difficult to kind of get an estimate of those that distribution and that density. So we used a remote sensing technique to get eye in the sky and see the overall distribution across the Falkland area. So we're using Sentinel-2 satellite imagery and using the differentiation of reflectance that you see from the kelp basically rafting on top of the surface as it floats up. And so you can see from this picture, it's fairly easy to differentiate between the kelp, the dark areas, and the surrounding deeper waters. And we verified that through drone imagery and then in-water ground truthing. And so once we have that overall layer, it's something like 830 kilometers squared across the whole of the Falklands. And you can see it's fairly dense in patches and surrounds the whole of that Falkland area. And so it's a sizable amount and surrounded by these deeper systems that will typically lead to sequestration of this resource. And so we were just looking at Macrocystis. So this is the really large kelp system, kelp species. But in the Falklands, you also have a number of underlying understory species. So the limitations of this method are that we're only seeing the kelp large enough to touch the surface or just below the surface so that it's visible from remote sensing. But there's a huge amount of underlying or understory production that's going on as well. And so these are other smaller kelp species such as Lawsonia or Davilia that also exist in that area. So if anything, this is underrepresenting by a fairly large amount of the deeper species that aren't being seen. And so we just did some calculations of essentially how many of these sporophytes, so the adult phase of the algae, we're seeing per meter squared, so density over the whole of the Falklands. And then we're figuring out how much biomass is taken up by each one of these whole kelp thalli or thallus individual. And then figuring out how much carbon is typically stored within each of those, when they're taken down to their essential elements. And so the overall calculation for that, the total standing stock that is currently there is around 0.22 million tons of carbon dioxide equivalent currently there. We then tried to think about the sequestration, and when we're using here known or published figures for the amount of net primary reduction. So this is also including some of the understory species that are found in that system, and using published rates of export to the deep sea or to the shelf in both dissolved and particulate organic carbon. And so these proportions, it's roughly about 10% that's drawn into these kind of deep sea. This is on a very general global basis. And so we're applying that to our system. And we excluded the amount that's buried in the surrounding shelf and the amount and all the aspects that are remineralized or grazed in that surrounding system. And once you do that each year, you're getting around a similar amount, so 0.239 million tons of carbon dioxide sequestered each year down into those systems. And so the final aspects of this estimation, we were trying to put a economic accounting element to this. So trying to see how much that stored carbon or sequestered carbon might be worth in terms of its social costs. So one of the ways in which people try and do natural capital accounting is to apply this idea of social cost of carbon. And so this is the kind of it's kind of an estimate of how much the economic cost of producing how many tons of carbon dioxide is emitted each year, and how much that costs to society and its sort of non-market impacts on health, environment, well-being, things like that, and how much that sort of future damage and mitigation costs of carbon dioxide might be to humanity in a sort of global idea, and then discount that to current day values. And so this is based on a number of assumptions. So based on what kind of climate scenario we're going to experience into the future. So whether it will be a low carbon output or as business as usual, how many people there will be in the world, and also how much these carbon dioxide is valued on market or non-market variables, and then applying this discount rate of how much it will cost now versus how much it will cost in the future. And I think the others might debate some of the ways that we can do these kind of valuations. So some people like to put it onto emissions trading scheme levels, so how much it might cost to buy your ton of carbon dioxide equivalent in terms of like the EU emissions trading scheme. But that then misses out non-traded elements that are emissions from things like agriculture and things like that, so not from industry. And then you can put them on different scenarios into present day or future day, future scenarios, and figure out how much that might be worth currently and then into the future. And obviously these are very subjective and kind of value-based analyses, and so they can be very changeable, but they seem to be worth a lot of money. So just as a summary. We found that Macrocystis standing stock in the Falklands was currently worth around 22 million US dollars, and then the annual sequestration of the deep sea was around 24 million per year. So that's including these other aspects. And the numbers aren't necessarily the most important thing. It's more that this appreciation of the value of these kelp systems globally, because they're a quite significant resource. And they're valuable in terms of this regulation and mitigation of future damage to our climate, and they should be more valued. And then finally, it's just worth remembering that these systems are really valuable in terms of many other aspects other than carbon. So, and that's what we're researching now, these many other ecosystem services that are associated with kelp systems. So thanks for listening, and hope we didn't run over too much. Thanks.
That's great, Dan. We'll move straight on to Tiziana to keep up with the timings, and then we'll do questions at the end.
So Diana already introduced me, so I can only say that today I'm going to talk to you about the carbon accounting for coastal and marine environments. So firstly, what are natural capital accounts? Natural capital accounts are a set of interrelated tables which provide a snapshot of ecosystem stocks and flows in physical and in monetary terms. There is some international guidance in line with the system of national accounts, which is so these three, the first three ones, the system of environmental economic accounting, central framework is the international guidance that gives the overall framework for environmental accounting. And the experimental ecosystem accounting is instead specific for ecosystem accounting, and the technical recommendations are in support of the experimental ecosystem accounting, so to explain even further how to operationalize the ecosystem accounts. We have also some specific UK guidelines provided by the Office of National Statistics, which are the principle for natural capital accounts. And can you click another 3 times? Another one as well? Thank you. So we have, no, I need to say something before. Okay, thank you. So we have also other guidelines from the UK as well. So the roadmap to 2020, and since marine and coastal ecosystems are treated not as deeply as the land ecosystems, we have in the UK some initial studies on coastal margins and ecosystem accounts, and the SIA as well has few marine and coastal ecosystems, but not all of them. And in particular for within the technical recommendation, it is clear that carbon sequestration is a thematic account, which means that it's one of the accounts that need more research, and for carbon sequestration in the SIA, it is meant the carbon sequestration, but also the long-term storage. Next slide, thank you. So, so as I was saying, marine and coastal natural capital accounts are are taking momentum now, and in the UK, JNCC and CFAS, as Diana mentioned before, developed an initial study to advance the development of natural capital accounts for the UK marine and coastal environment. This has been done in line with the 25-year environment plan and following guidance from DEFRA, ONS, and the CIA that I just showed you. Next two, thank you. We used only available data to provide the estimates and for the both the stocks and the flows of the marine and coastal habitats in the UK. And we provided an initial set of accounts, which included ecosystem extent and condition accounts. These ones are a set of tables in which the extent, so the area, and also the condition of the ecosystem that is under investigation. And we looked at salt marshes and shelf sea sediments and then we also provided some accounts, so some other tables for the physical and monetary ecosystem services accounts. So these ones provide the physical ones provides some estimates in unit measure. So for carbon is tons of CO2 equivalent, and the monetary accounts instead are presented using the currency of the country that is producing them. So for the UK, in pound sterling. Next slide, thanks. So what you're seeing now is the logic chain that we produced for the service of climate regulation, which is carbon sequestration and storage. This process of creating the logic chain is quite an interesting one because JNCC and CFAS, both natural scientists and economists, got together and we came up with this logic chain to come up with the value of the benefits that we were getting from the habitats. So we started looking at the habitat, and we used, to determine their extent, we used the UNIS, the European Nature Information System habitat classification, as I said, for salt marshes and shelf sea sediments. And then we looked at the characteristics of these ecosystems that were enabling the stock, so the ecosystem, the habitat, to produce ecosystem services. In this case, we were focusing on climate regulation to get the benefit of healthy climate. We also looked at the human and economic inputs, both on the side of the land use change, so the potential release of greenhouse gas emissions with land use change, but we also considered the opportunity of an ecosystem management of the area, including restoration and conservation. Next slide. Thank you. Thanks. So for the healthy climate benefits, for the shelf sea sediments, we look at the POC that was buried in the shelf sea sediments, and the way we estimated the value of carbon for the accounts was through the method that it's called damage cost avoided. So looking at the damage cost that is avoided preventing CO2 in the atmosphere. So we looked at the extent of the habitats, and we looked at the carbon storage barrel rate, and then for the monetary value of carbon, we used the abatement cost method, and we took the non-traded carbon central value provided by BASE. So the as you can see, the functions to get the carbon value to be inserted in the accounts, it's quite simple. So for the carbon benefits, we obtain that at time t. And this is important because for accounts, we are looking at specific years, 1 year on year. And so we don't have the scenarios as Dan mentioned before. And we have to use exchange values, and that's why we use the abatement cost to be in line with the system of national accounts. So the cost of the carbon benefits is then given by the carbon sequestration service, which is obtained multiplying the area of the ecosystems, both the coastal and then the marine, so the salt marshes and the shelf sea sediments, by their carbon barrel rate for different areas. So for the shelf sea sediments, for example, we looked at mud and sand, and the salt marshes around the UK. And this one is then multiplied by the value of carbon chosen. So can you click again, please? Yes, so as you can see, the value that we came up with between the years 2012 and 2017 are around 600 million, and the differences that you notice are because of changing in price year by year. And but we assumed a constant provision of the service for all of those years due to data limitations. Next slide, please. So the question is, why do we do natural capital accounts? Well, because there are several potential policy applications. So the first one is that especially disaggregated accounts may inform decisions about areas that are important in terms of services provided. So we can identify specific area where we want to do some management of the coastal and marine areas. And also, ecosystem accounts provide a broader view of the importance of the marine environment to economic and social development. So we can have an understanding of a proper, sustainable blue economy. Another click, please. So the last one is also that we can understand better the social context of the users and beneficiaries. So we can link our ecosystem services account to the users and the beneficiaries of those services, and that will help us to understand the social context better. And that is it. So thanks.
That's great. Thank you, Tiziana.
Hi, everyone. Good afternoon. As Diana has already introduced me, I'll get started straight away. I'm Professor Nicola Beaumont from the Plymouth Marine Laboratory. And my seminar today is a little bit different in that I'm going to provide a much more holistic overview, following on from those really excellent presentations from Tiziana and Dan. So I've entitled it An Exploration of Blue Carbon because I want to cover quite a lot. I think the first question is why? Why are we hearing so much at the minute about blue carbon? And it's worth taking a moment to think about this. I think a really key reason is because climate has become so high on all our agendas, both in the case of the general public, but also in the case of governments. The UK government late last year was the first to put through the net zero emissions law. And this has also been mirrored both in Europe and internationally. Now, this move, this drive to achieve net zero is really interesting for blue carbon because there's two ways to achieve net zero. One is to reduce the amount of carbon that we're emitting, and we hear a lot about that. But another is to actually manipulate our environments so they take up more carbon? So can we manage our environments to sequester and store more carbon going forward? And already there's quite a lot of energy around the idea of managing our marine and coastal environments to do just this. One of the ideas, for example, that's been brought back to the fore is this idea about, for example, fertilizing the ocean with iron to make sure, to try and help it to take up more carbon. It's very controversial as an idea, but it's interesting to see these coming back up. And we're also seeing blue carbon take a primary role in places like the IPCC. And across the climate agenda, I think there's a rapidly growing awareness of the role that the marine and coastal environments can play. So I think this is one of the key reasons why we're hearing so much about blue carbon at the moment. I think it's useful to take a second to think about, firstly, what we do know. And then once I've talked about what we do know, I want to talk a little bit more about what we don't know. What we do know, blue carbon, we talk about it a lot, and this is the fact that carbon is certainly being captured and sequestered and also stored by marine and coastal habitats and species. There's a couple of things in this first point. The first one is to understand and be clear that there's a difference between the carbon that's being captured and taken up and the carbon being stored. And it's very key to be clear on this. And I'll come back to this in the following slide. The second thing here, again, which is interesting to raise, is a lot of our discussions around blue carbon previously have been focused on habitats and different habitats' ability to do this. But increasingly, there's a discussion now around actual species' ability to do this as well. And again, I'll talk about that in a little bit later. What else do we know? We know that a huge amount of our anthropogenic CO2 emissions are sequestered by the oceans, at least a third, possibly more. So they're playing a very substantial role. Interestingly, we know that if we manage our environments to sequester more blue carbon, it doesn't just benefit us from a climate perspective. As Dan raised in his presentation, that these habitats provide a whole host of different services. And if we manage them to maximize their carbon sequestration potential, we'll also see benefits, for example, with regard to coastal protection and fisheries. And the final thing here that we know is that we're in a really interesting place. There's been work going on carbon sequestration storage by natural scientists and social scientists for decades. This is not new. What is new is the take-up by government, by intergovernmental bodies, by NGOs, by charities, by conservation organizations, by the private sector as well, and the general publics. So there's now a huge amount of energy around this. And this, I think, is interesting because it's a drive now for academics to really make their research be useful. We have to be able to communicate our blue carbon information, and we have to be able to communicate it in a way that's meaningful. These are some of the things we do know. We do also know quite a lot about where the carbon is in the environment and how the carbon is moving around the environment. This figure is actually 10, nearly 11 years old, but the fundamentals of it remain more or less the same. This is, I think, quite nice because it shows us what's happening in the ocean here on the right-hand side and in the coastal area, but also puts it in the context of what's going on land and in the atmosphere. The boxes that are coloured in show the amount of carbon being stored, and the yellow arrows show how the carbon is moving around the system. And this comes back to my point on the previous slide, the yellow arrows in particular. If we look for a second here at the coastal area, so you can see, can you see my mouse if I move my mouse? Okay. So in the coastal area here, we can see that there's 92 gigatons of carbon being sequestered every year from the atmosphere into the ocean, the coastal ocean, but there's 90 gigatons then being released back out again. And this is the point I was trying to make about the difference between sequestration and storage. And it's really key to understand this. We often see estimates of blue carbon relating to the amount being taken up, but without much discussion about what is then being released. And actually grasping these net figures as opposed to the gross is really, really important. So this shows us we know quite a lot about where the carbon is and a little bit about how the carbon is moving around the system. Not only do we know this, we also know a little bit about how we can put economic values on these natural science estimates. And this is data taken from a recent paper published in Nature Communications. And I think this really shows, and it builds very much on what Tiziana was saying, that we have got estimates of value per hectare for the different types of marine and coastal habitats. In this case, for tidal marsh, for mangroves, for seagrass, coastal plankton and deep sea. So we have a feeling for these numbers, and we can provide per area values in terms of money. Now, there's some issues with this, which I'm going to get onto. As I said previously, we've seen a lot of these generalized figures at habitat level, and what's been coming out recently more and more is also we need to take into account individual species. And the species which are of particular interest, I think, are marine mammals. We've just literally last week published on this in Conservation Biology. The reference is at the bottom, and I'd be happy to share this. And it's quite exciting, really, to start to think about these systems in this way. Dan was explaining how kelp hasn't really been explored very much before, and the macroalgae in regard to the role it plays for blue carbon. And this is similar. In the case of marine mammals, this is another species which has been mostly overlooked previously. So specifically looking at whales, our estimates show that if we saw a recovery of the Southern Hemisphere whale population, we'd see a huge increase in the amount of carbon being sequestered in the biomass. So that's the carbon being held actually within the whales. Additionally to this, whales not only hold carbon within their bodies whilst they're alive, they also play a really significant role in the amount of carbon sinking to the bottom of the sea, both through their feces and also when they die and their bodies sink to the bottom of the ocean. And the extent of this role, as you can see here, is looking like it could be really quite significant. We haven't really considered this before, and it's quite interesting to think about this, because if we start to see an increase in the amount of marine mammals in the ocean, we could see an accompanying increase of carbon being taken up and stored while the animal is alive, but also an increase in the amount of carbon sinking to the bottom of the sea and being stored permanently through the animal's life and also once it's died. Interestingly, the whales and marine mammals play quite a complicated role within the system. So it's not just about the carbon they hold and the carbon that is sinking when they die. They will have an effect on primary productivity within the ocean. They'll have an effect, obviously, on fisheries and other species. So they'll have a lot of follow-on effects from their activities. I think that we have got these initial figures now of understanding how marine mammals and whales in particular will affect carbon cycling, but the detail of it is something that we're still working on. There'll be a lot of probably other effects as well. So that's a bit about what we do know. And I think it's easy to fall into a trap of feeling quite confident that we've got a good grasp on these different figures. What we, coming back to a paper, like I said, that we published late last year, this paper was all about exploring what we didn't know. So we got a group of 50 academics together who work on blue carbon and asked them what the 10 key questions were for blue carbon going forward. And I thought this would be really useful to share with you today because it's quite a holistic approach. So I've just copied some. I'm not going to do all 10 of the questions. I'm just going to share a few of them. The first one is how will climate change impact carbon accumulation, both in mature blue carbon ecosystems and also during the restoration? And I think it's good to stop and think about this for a minute. The rates of carbon sequestration and storage that we have at the minute are largely based on the environment as it is now. Now, we all know it's very likely that we'll see significant changes in our climate going forward. We'll see changes in the seawater temperature, in potentially seawater acidity, a whole host of variation potentially ahead. And all of these changes could significantly affect the rates at which these habitats and species are accumulating carbon. It could be a positive feedback loop with more carbon sequestered and taken up, or it could equally be a negative feedback loop. We don't know. We don't know the answer to this. And this is a really important question going forward. Also included in this question is this idea about, will it be different between a mature system and a restored system? When we're thinking about net benefit, net zero, and achieving net zero, we're talking a lot about how we can manage our system differently in the future, and can we restore habitats to take up more CO2? Now, think for a second about a salt marsh. A very old salt marsh, a well-established salt marsh, has got much greater potential to take up carbon and store carbon than a newly restored one. So it's important to understand these differences. We cannot really say that a per hectare value for the salt marsh is appropriate for all. It will be different for an old salt marsh and a newly restored one. So there are these complications in the figure which need to be addressed and better understood. A second question was, how will disturbance affect the burial rate of blue carbon? Again, we talk a lot about how carbon is being stored, and I think we tend to assume that this will be permanent. Now, this isn't always the case. If we have big storms, we may see vast areas of salt marsh washed back into the sea, and all the carbon stored within then is re-released. If we see a lot of fishing activity, we can see the sediment, the sea sediment, being all stirred up and carbon being again re-released into the environment. So understanding this, understanding how these future disturbances may actually re-release a lot of that carbon that we have thought would be stored is very important. The third question relates really nicely, I think, back to Dan's presentation. And I think the role of macroalgae, as he was saying, in the carbon cycle has been really misrepresented and hasn't been taken seriously enough in the past. So it's really nice to see his research today. Understanding the role of these macroalgae was raised as a very key question in these, number 3 of 10. Fourth, what's the global extent and temporal distribution of blue carbon ecosystems? We don't know this. We've got quite a good grasp in the UK, but on a global basis, not so much. 7 was what factors influence the burial rates? Now, again, I think we have this idea that we understand how much carbon is being buried in the sediments. In reality, we don't know, and it varies depending on the biodiversity within the sediment, depending on the hydrology that's around the sediment, the chemistry within the sediment, and actually understanding this and the variance across the marine environment is very important going forward. And the 8th question here was understanding this that I raised earlier. What's the net flux of greenhouse gases between the seas and coastal habitats and the atmosphere? We don't just need to know what's taken up, we need to know what's released as well, so that we can make sensible decisions. Now, there's 2 more questions on this list. One is about uncertainty and one is about management. And I worked on the first one, and Tiziana, I know, worked on the second. Understanding the uncertainty around these blue carbon numbers is very close to my heart, and I've worked on this for over a decade now. We often see figures like the ones I showed earlier in my presentation, and like the ones in Tiziana's presentation as well, where we have a bar chart that shows us specifically how much carbon is being sequestered and stored and what the value of this is. These are great, but it is really critical that we understand there's actually a lot of uncertainty associated with this. There's uncertainty in the sequestration rates, and here I've just copied a few of the sequestration rates that I've used before, and you can see for dunes and Maca and salt marsh in the UK, there's quite a large level of uncertainty around the sequestration rates. But as Dan showed in his presentation, there's also a lot of variation in carbon price. It depends which carbon price you use. Do you use a social cost or a margin, an abatement cost or a carbon price? There's a whole host of choices. And you can also vary the outcome by discount rate. And we know for a fact that when we show you these values, when we share these values of this is the value of salt marsh for carbon sequestration, it's easily out by an order of magnitude. And just to demonstrate this using some real life data, this is work that I undertook on UK coastal habitats. And this is the value per year. And it's a combination of sand dunes, salt marshes and macaire. And here the red bars show the lowest potential value. And this is if we take that really low sequestration rate and a really low carbon value, low carbon price. And the green bar shows the highest values. This is taking the highest sequestration rate and the highest economic value. And in 2010, you can see that the value for the UK coastal habitats could be anything between 5 million per year and 50 million per year. Going forward to 2060, it could be anything between 25 million per year and 250 million per year. Now, the bars that we tend to share are the blue bars in the middle, but I just wanted to take this time to show you there's actually a lot of uncertainty around this, that we need some help, I think, in how we communicate. There's additional uncertainty as well here, that we don't know what will happen with climate change. We don't know how permanent the storage is. The amount of carbon sequestered will vary hugely by species and by scale. So actually, this is showing you an order of magnitude of uncertainty. Once you include all these other uncertainties, that goes up even more. So key questions that really interest me going forward are: how much uncertainty is acceptable, do you think? And how do we communicate? How should we communicate and visualize this uncertainty? And how, going forward, can we reduce this uncertainty? I think we've got enough to know that we should be using these values, but I just think we need to think more about this uncertainty. So the final question was about how, in the top 10 questions, was how do we manage, how are we going to manage the environment to sequester blue carbon going forward? And there was 3 real ways to this: we can preserve, we can restore, and we can create. The discussion about this really is in its infancy. There's work going on, and I'd be happy to talk about that more in the future. So my 3 take-home messages today. The first one is we know a lot, which is great, and marine and coastal habitats clearly play a very significant role, and we've got some baseline estimates of both the potential and also its value. There are second take-home messages. We can manage our environments to enhance our blue carbon potential. So we can use this as a strategy in achieving net zero, which is really exciting, but we must be careful that we're realistic about this and we avoid unintended consequences. And the final take-home message is obviously around the uncertainty that I've mentioned. It doesn't have to preclude us from using these figures, but it does remain significant. And I think we need to think how we can incorporate this uncertainty in decision-making going forward. And that was all. So thank you very much.
That's great. Thank you very much, Nikki. And we have got 5 minutes for questions. We've had quite a few come in already. I'm just going to pop one up on the screen for, I think, firstly for Nikki's attention and then for the others as well. And then I'll pop up what comes in through the chat box. I'm just aware there's 75 people roughly on the call, so try and make your questions as concise as possible. Thank you. There we are. I think you should be able to see that now.
Okay, yes, this is true. We can possibly expect carbon prices to crash. This is a real risk, and there is a risk for blue carbon investments. This is where it's really important that we use a variety of different values, I think, to put monetary value on carbon. So we can use, like I said, we can use abatement costs, we can use carbon prices, we can use the social cost of carbon. All of these we can use to provide a price per tonne of carbon. And I think now is clearly the time when we're going to have to reach out and think about using a variety of these methodologies rather than just using the carbon prices, because there is an implication of this. But it doesn't have to be entirely negative. It could be switched to be more positive by forcing this debate really about the different prices of carbon, the different valuation methods for carbon that we have. But Tiziana may well want to comment on this as well, I think.
As Nikki was saying, there is this range of prices that we can use. In the question we are addressed about the price of carbon. So I think you're thinking about the EU ETS market, for example. So those prices are not really used when we are doing some policy evaluation. For example, we would use more the social cost of carbon that was presented by Dan if we wanted to look at policy options, because we look into the future, we look at scenarios. As Nikki was saying, we use a discount rate, and the social cost of carbon is a shadow price. So it is obtained, as Dan was saying, through modeling, looking at what would be the future, and so what could be the cost in the future of future generations in terms of health and the disruptions that could be created. And so a cost of carbon is obtained. Maybe, yes, probably new models will have to take account also of the pandemic, and it will change the value. But for example, the abatement cost instead is looking at what is the cost of really trying to reduce the impact of greenhouse gases. So it is another way, and this one is the one that I presented for the natural capital accounts, because it is an exchange value. So it is more related to the market, but is not the price of carbon in the market. So I hope this clarifies a bit.
That's great. Thank you, Tiziana. So we've got 4 questions just to begin with that I'll pop up on the screen. There's a couple for Dan, and then one for Nikki and everyone, and a final one to all speakers. We'll see how far we get with those in the next minute or so, and then we can extend and or close. Bear with me one moment. There we are. So Dan, the first 2 are on key ecosystem services and threats. So feel free to go ahead.
Yeah. And just before I go as well, I've been noted that I forgot to mention the funders and collaborators of my project, which was Darwin DEFRA funded project, EU Move, and Oregon State University, which did some of the modelling. So apologies to all of those if I didn't mention them as I rattled through earlier. Yeah, so ecosystem services that are being assessed as well now. So we're trying to include looking at the fisheries, which are the commercial fisheries, which are in the Falklands, which are heavily reliant in terms of nursery grounds and breeding grounds in terms of their life cycle. Also looking at nutrient cycling, so how much like is taken out through cycling within these systems. And we're touching on whether we can include these sort of cultural aspects and the non-use value of this ecosystem as well. So in terms of the next question, actually, some of the threats, some of these ecosystems in areas like South Africa and California, they have direct extraction in terms of harvesting of the kelp for alginate, which is like a chemical used in industry. And so while they don't have that currently in the Falklands, they had that historically. And it's quite a valuable resource. So that's one of the impacts. There's also kelp systems are affected by climate, as most things are, intense heat waves, as well as perhaps in a positive way, they're experiencing tropicalization, where they're spreading into new into areas that they couldn't exist in before. And similarly, they're getting expanded upon by coral reefs, which are spreading their range into kelp systems. Also, overly extractive fisheries can influence the ecosystem structure within kelp forests, as well as coastal development and direct harvesting. So there's a range of human pressures as well as like larger environmental pressures, but perhaps unusually, like they're fairly stable at the moment in terms of their global distribution. But as things warm up, that's likely to change in terms of where they are and how healthy they are as well. So if it gets too hot in terms of large heat waves, they can be impacted as well. Does that answer the questions?
That's
And
brilliant.
if they're degraded, they have less chance of being able to sequester carbon. Yeah.
Brilliant. If we move on to the question for Nikki.
Hi, yeah, I think, well, Dan sort of covered this a little bit about the impacts of climate change and changing ocean circulation patterns. I think the climate change impacts are really broad ranging. I think for some areas, for example, seagrasses actually thrive under increased acidification. So they do much better under some future scenarios where we see the oceans becoming increasingly acid, and with positive effects, the amount of carbon they can sequester. We have got a flip side of that, which is more storminess potentially, which can have a negative effect on salt marshes, particularly salt marshes which have got seawalls behind them, because they're a lot less resilient to sea level rise and stormy conditions. So a negative effect potentially on salt marshes. With regard to actually the circulation patterns and where the carbon is moving within the ocean and how it's moving and up and down to the sediments, again, I think it will be very variable depending on the area, with some areas seeing an increase in the amount of carbon that is taken up and then permanently sequestered, and other areas seeing a decrease. We tend to see at places where there's ocean fronts and there's more productivity and therefore more phytoplankton and more uptake of CO2, those fronts may well move and are expected to move, and therefore we'll see a move in where the carbon is being sequestered. This then may influence how much of it is then sinking and taken down to the deep sea. So a whole host of possible positive and negative effects, and I think that's really why in the paper it came out as one of those top 10 questions, is because we can say a little bit about some of the positive effects, a little bit about some negative effects, but we don't have a holistic overview yet of what the picture will be.
That's great, thanks, Nicola. Are there any other comments from Tiziana and Dan? We've got this question on phytoplankton left and 2 others if you're willing to stay on. I'll just pop them up in a minute.
I think it's a bit mean to say that phytoplankton don't do much.
Yeah.
I think there might be some argument about that from some people. I don't think it's necessarily, I mean, Dan, I think probably can speak more to this than me, but I don't think it's necessarily a trade-off between having phytoplankton and or offshore kelp farms. I think probably, Dan, we could have both.
Yeah, I mean, yeah, I think phytoplankton are important, as you say. And it's more really about valuing, the systems that we have globally, and sort of not sort of missing them off the, the list of how important they are and the services they provide. I mean, yeah, if floating kelp farms were able to be installed without damaging other ecosystems, yeah, it'd be great. But yeah, obviously there could be some pros and cons in that. But yeah, it's more about really protecting the existing kelp forests that we have in their natural location, and perhaps rebuilding areas that have been degraded. And that applies to any coastal ecosystem, such as seagrass, which have been massively reduced in their extent, and mangroves. Yeah, so I mean, the first one, we think that the dominant way in which they're sequestered long term is by being drawn down into these deep sea areas, so like taken off the continental shelf and down into deeper areas where you don't get this kind of as rapid mixing within that layer, so you don't get these as much movement and recirculation of these sediments. So they just settle down and get layered and layered and layered in these deep areas. But they also, there is some in some kelp forests, they have a larger amount of sediment surrounding them. In the Falklands, it's quite scoured, rocky shore, and so they don't typically get sequestered in that continental shelf so much, but they'll be taken down into the surrounding systems.
Brilliant, thanks, Dan. I don't know if Tiziana or Nicola wants to have a go at this last one.
Yes, I can say something if you like for the last question. Well, there aren't many blue carbon markets, and at least I think it has been addressed just on the coastal areas for salt marshes, wetlands, and mangroves. So for the deep sea beds, I think that there is a lot more uncertainty there. So as Nikki was pointing out, we have to reduce that uncertainty before any carbon markets can take off, I think, for those ecosystems as well. But at the same time, as Dan and Nikki were pointing out, there are lots of co-benefits in the ecosystems that provide carbon mitigation potentials. So there could be ways of funding MPA management if probably there would be the possibility of looking at composite payment for ecosystem services. So trying to address the value of the different benefits provided from a certain area of the sea. So there are examples of these around already. So I don't know if you heard about blue bonds, for example, or other composite payment for ecosystem services.
Brilliant, thanks Tiziana.
I want to thank our speakers very much. I found all these presentations immensely interesting and very informative. It's a new area for me. I'm not a marine specialist. So I hope that all the other people who joined were as pleased as I was about the how well the presentations went. And I think you did an excellent job managing it, Joe. So you all deserve a very big hand. So
we've got a couple of thank yous coming in on the questions.
Thank you very much. And we will look forward to seeing lots of people at the next Locked In Natural Capital Seminar webinar. Thank you very much.